Well, thanks very much for the invitation. It's nice to have the opportunity to talk to all of you today. So I often, or sometimes I start my talk with a slide that looks something like this, and people wonder if the projector is working correctly or what's going on. But the point I'm trying to make by putting up a slide like this is often, kind of the view of the world that we have as geophysicists. We're often missing pieces of the puzzle. What we do see is kind of distorted or blurred. And, not only is this a frustrating situation, it also impairs our ability to understand the processes that are happening within the Earth. And so I guess in the best case, we can, acknowledge and fully understand the limitations that we have in our view. And, in the worst case, we may think that our view is better than it is, and that may lead to erroneous interpretations. So I'm going to be talking about earthquake swarms. And, I guess the goal, or one of the goals that I have in this talk, is to show some of the ways that we can start to fill in these missing pieces and sharpen our view so that we can at least have some sort of basis for starting to understand, these physical processes that are happening deep within the Earth that we're so interested in trying to understand. So I'll acknowledge just in general here that much of this work is work with many different collaborators. So, you can blame me for whatever's in here, but you have to give them credit for much of this work. Okay, so I've had the wonderful opportunity over the last 10 years or so to look at a whole bunch of different earthquake swarms. Can you see the mouse here, or should I change the pointer to?
I see it. It's not real big, but I can.
Okay, well, let me see if I. Okay, maybe that's a little better. I don't know. Anyway, all of these squares on this map and this map over here are, earthquake swarms of one form or another that I've had the opportunity to look at, in more detail. And these are a mix of volcanic and tectonic or non-volcanic earthquake swarms. And there are some sort of overall patterns, some common themes that start to emerge from these earthquake swarms. We tend to see pronounced spatial temporal expansion. More often than not, we see overall upward migration of seismicity over the course of the swarm. And in many cases, we see evidence for complex faulting geometry, that is fracture mesh type faulting geometry on a variety of scales. So many of these swarms we've interpreted to involve fluid pressure transients, mostly with an aqueous fluid. Now, I don't have time to talk about all of these today, but I'm going to just highlight a few of them over the course of the talk. I'll start out by talking about the Kilauea sequence from 2018, the really fascinating eruption and seismicity sequence there. Then we'll move to Long Valley caldera and talk about two nearby but very different earthquake swarms that happened in 2014 and 2017. And finally, I'll talk about most recent work looking at a swarm, or a swarm-like sequence, I guess you might say, near the Makima Fault in Northern California. So the work I'm going to be talking about today is, we're working on earthquake detection, location, and at least toward the end, focal mechanisms, trying to get a sharper view of seismicity. And basically all of these techniques, all of the work that I'm talking about is relying on this underlying premise that nearby earthquakes usually exhibit similar waveforms. And what this means, I guess the reason this is because most of the complexity that we see at high frequencies for micro earthquakes is not complexity in the source process, it's complexity from the wave propagation. And in particular, much of the complexity comes from near the receiver. So we can exploit these waveform similarities, like I said, for event detection via matched filter, using routinely cataloged earthquakes as waveform templates. We can use this for precise relative relocation by aligning waveforms using cross correlation. And notably, these techniques can work even if focal mechanisms are dissimilar. And again, that's because most of this complexity is coming from the wave propagation rather than the source itself. And I'll use this toward the end to talk about some ways that we can actually get better constraints on the focal mechanisms and how they vary in some of these earthquake swarms. Okay, so just the basics on how we're detecting events. So we're using routinely cataloged earthquakes and the associated phase picks to form waveform templates. This figure shows an example, I think this is from Mount Rainier, where the P wave template is in red, the S wave template is in blue. So we take this waveform template, we scan it through the continuous data. So we're calculating a cross correlation at every lag time, usually incremented at 1 sample or 100th of a second. And then we identify times of high summed cross correlation across the network. So here's an example of this waveform template superimposed on a smaller but similar event in the continuous data. So the template is the red and blue waveforms, and the gray underneath is the smaller but similar event. And this plot on the lower right is showing the cross correlation functions separately for the S wave in blue and the P wave in red for each different station, and then the summed correlation in bold at the bottom. And here the time scale is plus or minus 4 seconds. It looks like on this time scale that all of these peaks are lining right at 0. And if they were truly at 0, this would indicate, that these two events are in exactly the same location, that there's, the lag times, the pattern of arrivals across the whole network is exactly the same. But what happens if we zoom in on this? So this lower plot is showing this time scale blown up to plus or minus 400ths of a second. And then the cross correlation function has been changed to show the shading here. And then the blue and red bars are showing the difference from a 0 lag to the peak of the cross correlation function. And you can see that even though these lags are small, many of them are even less than 100th of a second, these lags are reflecting the relative location between these two earthquakes. And in this case, these two earthquakes are about 37 meters apart. That's the relative difference in location that we get when we combine measurements like this from all the waveform pairs. So we take these lags shown in the red and blue bars, and we can directly input these into, in this case, HyperDD, double difference relocation algorithm. We're interpolating to get subsample precision. In the best case, we're getting something like millisecond precision, should be about 1/10 of a sample. And this allows us to get really precise relative locations for these events. And we're combining these relative measurements between hundreds, in some cases, thousands of, between hundreds and thousands, hundreds, some cases, thousands of templates, and many, many detected events in the continuous data. Okay, so that's kind of the basics of the first part of what we're doing here. Now I'm going to go through a few different examples. I'm going to show 2 examples of what I'm calling atypical swarms, and these are ones that, stand out. They're, really interesting processes, but they aren't the kinds of things that we're seeing, over and over as we look at earthquake swarms. And the first of these is the Kilauea 2018, the summit collapse. So, caldera collapses don't happen every day. So this one is pretty interesting, that was captured so well with so many seismometers located close to the sequence. And in fact, I was working on this as the summit collapse was underway. So I was kind of iterating earthquake detection and relocation, and HBO was using these relocations as part of their, real-time interpretations of what was going on. So this was an incredibly active sequence. So magma was erupting out the east rift zone here on the, I guess, on the inset map, quite a ways away from the summit zone. But for me, as a seismologist, I guess the most exciting part for me was the summit collapse. So that was happening, right at the Kilauea summit. There was a really great seismic network, as I mentioned. So we looked at April 29 to August 6. This encompassed, essentially the entire summit collapse sequence. We used 2,800 routinely cataloged events as waveform templates, and we used those to relocate more than 44,000 earthquakes during this sequence, with magnitudes ranging from -1 to 5. To put things in perspective, so I should have said this is a map view on the left and a cross section. The original profile here, this is 2009, but it was the same profile until shortly before this, or until the summit collapse started. And then you can see the difference in the profile as of August 11th, 2018. So just in the several month sequence in mid 2018, there was up to 500 meters of subsidence within the summit caldera. So 500 meter subsidence over 3 months, just to put that in perspective, that's about 50,000 times the San Andreas Fault slip rate. So in that context, maybe it's not surprising that there was a lot of seismicity. And in fact, this 44,000 events is what we thought we could precisely relocate. We detected more than 200,000 events during this, 3+ month time period. And the collapse zone kind of progressively enlarged, and the seismicity would start up kind of outboard of where the collapse had extended. But by the end of the sequence, this is the kind of the final digital elevation model showing this seismicity kind of outlining the eastern edge of the collapse zone.
Yeah, David, could I ask a quick question?
Yeah.
How do you deal with the changes in velocity structures and things collapsing?
Yeah, that's a good question. We, the short answer is we didn't try to deal with that. I think on short time scales, it may not be a big issue, but it's probably something that should be looked into more as part of this. I'm not, and maybe that's been done subsequent to this work. I haven't totally kept up on, there's been a ton of literature on this eruption sequence.
Okay, thanks.
Okay, so the temporal patterns of seismicity were really fascinating as well. Okay, so on the left is a map view and cross section again. Here I've color coded events by groups of events with similar patterns of phase polarities across the network. This will make more sense maybe toward the end of the talk. But basically, you can think of these as groups of earthquakes that have similar focal mechanisms. And in this case, it's kind of just useful for getting an idea of the different zones of seismicity. I probably don't have to worry too much about the details in this case, but the colors on this left map and cross section are the same as the colors on the right-hand plots. This is starting in May on the top through June and July into early August, I guess. So in early May, there was this magnitude 6.9 earthquake on the south flank of Kilauea. That's this red bar here. And then the subsequent black bars are, there was a repeated sequence of magnitude 5+ essentially collapse earthquakes. And the early collapse events had, big ash emissions. Those sort of, the ash emissions reduced over time, but the collapse events continued at pretty regular intervals. You can see here, ranging from, I believe 24 to 36 hours during this most active period, kind of in the June, July timeframe, and then kind of stretching out toward the end. The early ones were a little more irregular in time. But the main pattern that we see with the seismicity is that you would have the seismicity would increase, ramp up to some level, you would have a collapse event, and then essentially the seismicity would shut off for a time period of perhaps a few hours. That time, varied somewhat depending on which part of the seismicity zone you were looking at. So I think I can give you a better sense of what this looked like by playing an animation.
Hey, Dave, can I
Yeah.
ask a question about that slide before you go? Because
Yeah.
you didn't mention it, but it looks like the depth of those different sequences increases with time. So like, is it a real effect, or is that something you're not sure about?
Yeah, I think my sense is that the overall deepening with time is a real effect. Is that this whole, there was a big zone that was essentially sinking down in, and there were sort of faults within faults. So it'd be natural that, the faults themselves were moving down.
Mhm.
But as I think John was asking about the possible velocity changes could have affected some of these short-term patterns of depth, I think. So I think that's something we need to look into a little bit more to, before I really want to stake a definite claim on the deepening there.
Got it. Thank you.
Okay, so I'm going to show an animation here. The top plot is the map view showing the summit area of Kilauea where all the seismicity was. The bottom is the cross section. It's this cross section AB, which is going to spin around to give you a little bit of the sense of the three-dimensional structure of this seismicity. Future events, that is, events that are going to happen, are in white. Events that are in the past are in black, and then events in this 6-hour moving time window are going to be red at kind of the leading edge of this event and transitioning through this color spectrum to blue to help you kind of track the migration. Let me go ahead and start this. Let's see here, maybe. I need the arrow here to start it. Okay, so there's a whole lot of seismicity going on here. Each time this turns black, and you may see these the big circles, that's one of these magnitude 5 collapse events, the circles are scaled, according to sort of, I'll say, a naive estimate of physical source dimension, just assuming a 3 megapascal stress drop. But it gives you a sense of sort of the relative size of some of these events. So you can see seismicity ramps up, the collapse event happens, things get real quiet for at least a few hours before they start ramping up again. Especially if you look here in map view, it's playing a little bit jerky on my end, but you'll start to see sequences of very rapid, repeating earthquakes. So you see these concentric circles popping off over and over again. Like I said before, this, the slip rates, if you imagine that, the entire 500 meters was accommodated on a single fault over those 3 months, it's 50,000 times the San Andreas slip rate. So, these are repeating earthquakes on steroids compared to what you might see on the San Andreas. You have magnitude 2s and even magnitude 3 repeating earthquakes just popping off very rapidly along this this rim of at least of the eventual collapse zone. So these sequences are just happening over and over. Things start going a little bit more rapidly. Now we're into mid to late June here. So the sequence has been going on for over a month. And these collapse events were big enough that they actually caused, a lot of damage to the Hawaii Volcano Observatory facility that's located just up here on the rim of the caldera, or I should say used to be located there. That had to be abandoned. And now you can see that this seismicity is even more intense. You can see just these rings of repeated seismicity, similar magnitudes happening over and over in the same place. So this doesn't go through the entire eruption. I think this animation stops at the end of June, but you can imagine a whole nother month of kind of similar activity like this. Just a huge amount of seismicity. Okay. So our conceptual model for what was going on here, this is a very simplified model, but essentially this is the Kilauea caldera. There's magma underneath some sort of piston-like block here on the top. This magma is being withdrawn as it erupts out the east rift zone, and that probably causes areas of reduced gas and magma pressure within this piston itself. There may be dikes and sills that are starting to close in response to this pressure decrease. The magma withdrawal continues, and you start to get slip on the boundaries of this piston like structure. And then finally, you get one of these collapse events, and the system essentially resets itself for another round of this kind of behavior. Okay, so that's it for Kilauea. I'm going to move on to Long Valley caldera. So I think many of you are familiar with the location of Long Valley. San Francisco is here for reference. So it's essentially straight east of San Francisco. The Long Valley caldera formed in a giant volcanic eruption about 767,000 years ago. And I'm actually going to highlight two different swarms, only about 10 kilometers apart, but very, very different in terms of the processes that we think are active. So the 2014 swarm was within the caldera itself, kind of in the South Moat area. And the 2017 swarm was in what's sometimes called the Sierra Nevada block, beneath the Sierra Nevada mountains, south of Long Valley Caldera. So we'll start out with this 2017 swarm. So this is, I'll call it atypical swarm example number 2. This is a swarm that we think was actually triggered by large amounts of snowmelt infiltrating the subsurface in this area. And this was an interpretation that I was pretty skeptical of at first, but I think the evidence bears it out. This was work that was led by Emily Montgomery Brown. And she was the one who really, identified this pattern to begin with. So I think this is a really fascinating example because it defies what, at least my expectations about what kinds of, the kinds of timescales that we expect fluid to infiltrate into the subsurface and the processes that we expect to be important for earthquake swarms. So this, let me start with this plot on the right. The plot on the right is showing earthquakes starting at the beginning of 2016, going through 2017. Earthquakes in this Sierra Nevada block. I believe these may be the earthquakes that are relatively shallow, 4-kilometer depth below surface or less. And superimposed on this plot is the blue line is the stream flow at Hot Creek, which is in the caldera, and the red line is the groundwater from the water level in a well located near the southern boundary of Long Valley Caldera. So this is pretty interesting. It looks like a little bit after this big hydrologic spike, there's a spike in seismicity, and this the peak snowmelt is happening in the very late spring, early summer, and the peak in earthquakes was happening in the early part of the summer. This is kind of interesting, but based on this plot, I would have just, attributed this to, random chance. Oh, you happen to have an earthquake swarm as, the snow melts in the spring. Maybe not too remarkable. But we started to look into this more, and it became more interesting. So the map here on the left is showing the location of this earthquake swarm. It's just south of Convict Lake. It's near the site of where there were several magnitude 6 earthquakes in 1980. There's been a lot of seismicity in this zone, and some of it we think may be related to the volcanic system. So we were interested, especially in figuring out whether this swarm had anything to do with activity in the volcanic system. So what we found when we relocated the seismicity from this sequence is that the seismicity, for one, was very shallow, and for two, it had a clear downward migration trend. And this is the opposite migration trend from what we typically see in these earthquake swarms, in earthquake swarms in general, I guess. This plot is showing a map view of this sequence. The events are color-coded with time, in this case from late May into mid-June, from blue to red. And the cross-section especially, I'll draw your eye to that events are aligned along a fault that's steeply dipping to the east. And there's this clear downward propagation of seismicity that you can also see in this top plot. Top plot is event depth versus time. And the depths here are relative to the mean surface elevation, which is nearly 3,000 meters above sea level in this area. So these are quite shallow. Sea level would be down here. So at the same time, we look back at the historical data. In fact, there's good data back into the mid-'80s in this area. So we had 33 years of historical data. And what we found was that this pattern of earthquake sequences accompanying snowmelt, particularly snowmelt in very wet years. You know, this area of the Sierra Nevada gets a huge amount of snow in some years, that we see those accompanied by spikes in seismicity. And we've seen this several times over the last 33 years. You know, just sort of anecdotally, it seems like this feature is especially pronounced when you have a very wet year that's followed by, a very wet year that follows maybe a series of dry years. And again, the blue line is the water level in this Hot Creek flume that's located in the middle of the caldera, and the red line is the water level in this SC1 well at the southern boundary of the caldera. So this is starting to look a lot more convincing. You know, we have this 2017 earthquake swarm that's very shallow that migrates downward with depth. We look back in time, we see that this pattern has repeated itself. But we wanted to look at it even in a little bit more systematic way. So this plot on the lower left is showing we essentially binned all the time by stream flow percentile. So this is percentile from 0 to 100 on the x-axis, average numbers of earthquakes per day on the y-axis. And you can see not only does seismicity increase at higher streamflow rates, but it's a very systematic increase with percentile. So we have a lot of days that are relatively dry. These are still quite low streamflow rates up to this kind of 60-some percentile here. These have relatively few earthquakes. And then we have a smaller number of very wet times that have a whole lot of earthquakes. And in fact, if we compare the wettest bin here, the wettest 5% to the driest 5%, there's 37 times more earthquakes during wet days than dry days. So, you know, typically when people are looking for a hydrologic connection between seismicity, you know, we're doing lots of statistical tests. It might be a few percent effect. This is not that kind of effect. This is a huge effect. They're a factor of 37 more seismicity during these wettest times compared to the driest times. And we can see that the lag between the peak of the hydrologic signal and the peak of the earthquakes is something ranging from about 2 weeks to a month, with a mean of 24 days. So this is a pretty short lag time for water to infiltrate down to seismogenic depths. So how can that happen, and why does it happen here? Well, it turns out that there are some pretty unusual geologic circumstances in this area of the world. For one, we have this roof pendant sequence. So these are old kind of tortured rocks that are above the Sierra Nevada pluton. These layers are tipped so that they're the bedding boundaries are steeply dipping, and these boundaries between the geologic units may have very high permeability that allows rapid infiltration of snowmelt from the surface. And in fact, when we superimpose the relocations, I swear I did not manipulate this to make it line up better. We see that the seismicity appears to align along the down dip extension of perhaps one of these bedding interfaces. So it looks like we're getting a lot of water from snowmelt. It's infiltrating in an area of very high permeability because of the geology, and it's quickly getting down to depths where earthquakes can be generated. And so I guess it must be some combination of this unusual geology with relatively high strain rates that makes it so we see this pattern in this area. Okay, so I'm going to stay in Long Valley, but move to a very different kind of swarm. So in 2014, there was what seemed like a pretty exciting earthquake swarm. It was right in the caldera. It had earthquakes that were up to magnitude 3.5, which is large enough to be felt. And even though as seismologists, we might not draw a very sharp boundary between earthquakes that are too small to be felt and those that are large enough to be felt, that boundary is very pronounced for residents in the area and for the media. So this was an earthquake swarm that got a lot of attention at the time, people wondering what was happening and, was the volcano about to erupt? Of course, we didn't think that it was close to erupting. We know that Long Valley has had lots of big seismicity sequences in the past. And in fact, many calderas around the world, are capable of generating a lot of seismicity, without indicating an eruption. So let's see. Yeah, this earthquake swarm here is a map view showing the earthquake swarm location within the Long Valley caldera, which is outlined in purple. The lower plot is showing the seismicity sequence from the beginning of June through October. And you can kind of see that this sequence, you might call it a swarm of swarms. There were these smaller seismicity sequences early on. This one in July, we thought, at the time was a swarm unto itself. But then, little did we know that toward the end of September and in early October, there would be a much larger and more active sequence that would happen very nearby this earlier activity. So there were more than 3,000 cataloged earthquakes that we used as waveform templates. We detected and precisely located about 8,500 events after processing. And actually, we also looked at magnitudes for this sequence, and we got magnitudes for more than 18,000 events. It turns out it's a lot easier to get a magnitude or a reliable magnitude for an earthquake. You don't need as much data as you do to get a good location for the event. So this is showing an animation of the routine cataloged earthquakes on the left and the detected and relocated catalog on the right. This is just to try to convince you that, we're not totally wasting our time in working on getting a better catalog for this sequence. You can imagine if you're trying to interpret physical processes based on the catalog on the left, you would have a pretty tough time. It looks like a, kind of vertically extended cloud compared to on the right, where you can start to see, discrete fault features and migration of the activity with time. And this sequence in particular had some really interesting spatial temporal migration. I'm going to show that July, I guess, subsequence, you can call it, subswarm. The plot here is showing distance from the first event with time and a couple of diffusivities just for reference that I've put on top of this. The bottom plot here is showing event depth with time. And this is actually a common pattern that we see, where we see initially both downward and upward migration. But the downward limb, you might call it, peters out quite quickly with time, whereas the upward migrating limb continues much longer. This is kind of pattern that we see in several different swarms, and maybe it's at least consistent with the kind of thing you would expect with fluid pressure transients, where you see this kind of overall upward propagation. On the right, I'm going to show an animation of this July subswarm. The top is a map view that I've rotated with north to the right, just so that it corresponds with the cross section down below. And as I start this, you'll see what's initially a very concentrated zone of seismicity. and it'll expand outward kind of episodically with time. You'll see, maybe a somewhat larger earthquake with aftershocks rimming the source zone of that earthquake, and then it'll maybe pause for a second, and then you'll see another little bit larger earthquake, and the same thing repeating as it expands outward with time. And you can imagine just kind of hooking up a fire hose to this fault at this initiation point here. And probably what this is reflecting is that, as we get these seismicity, it's likely that the permeability is increased dramatically in the zone that slipped. This could allow fluids to diffuse into that zone pretty rapidly, and starts triggering more earthquakes on the fringe of the previous activity, and continues as long as that fluid pressure remains elevated and the stress remains near critical. And again, this kind of a pattern is what I would say is the typical behavior in many of these swarms that I've looked at. And again, the circle size is an approximation of the physical rupture dimension of the events. Okay, so one thing that we were interested in doing here was to get better constraints on the focal mechanisms. It's great to have precise locations for the earthquakes, but if we can understand the sense of slip in addition, then that will give us a lot more information about what's going on. So as part of this swarm, we worked on a technique to use essentially the relative polarity of P and S waves between the template and the event in the continuous data as determined by the cross-correlation function. So this is an example showing a waveform template, the orange and blue here overlaid on an event in the continuous data. And you can see it sort of corresponds, but it doesn't match so well. But when we flip the polarity of the template, in this case, we flip both the P wave and the S wave template upside down, we can see they match a lot better. And that same thing is reflected here in the bottom plots that are showing the cross-correlation function. Here, I've just flipped the negative part of the cross-correlation function upside down so you can compare its amplitude with the positive part. So essentially, we do two things here. We allow negative cross-correlation peaks in our overall processing for detection and for relative timing. And then we measure the sign of that peak absolute value correlation, and we compare the amplitude to the secondary peak. And we use that as a proxy for the confidence in how confident we are in that relative polarity between events. And I don't have time to go through the whole technique of how we boil stuff down, but essentially we have millions and millions of measurements like this. And even if individual measurements are noisy, we can boil down all of that data into something that's pretty robust. So essentially, this is taking advantage of the same, principle that I talked about before. In the extreme case, if we have two earthquakes that are on the same fault, but one slips in the opposite direction, it's going to generate identical but opposite in polarity waveforms. Okay, so here's the results that we get from this processing. And again, I'm skipping several steps here, but this is a map view and a cross section. The events are color coded. We are grouping events by those events that have similar patterns of polarities across the network, and then we compute a composite focal mechanism for those groups. So these are the focal mechanisms that correspond with events with the colors that they're plotted in here. And most of these are left lateral, seem to be left lateral north-south striking faulting. But there are a few, in particular the yellow here, that appear to be right lateral faulting that's instead striking toward the northwest. So it's pretty interesting if you compare the dark blue and the yellow here. These are, not quite opposite, but very, very nearly opposite senses of slip. And these two faulting orientations are essentially coexisting in close proximity in this area. So one of the interesting aspects of this is that we see evidence for a small but persistent mismatch between the faulting orientation as defined by the focal mechanism and the orientations defined by seismicity. And I didn't mention it before, but the black line overlaid on these focal mechanisms is a visual estimate of the seismicity orientation associated with these. So this mismatch, we've looked at it. It could be, it could just be uncertainty, but there's reason to think that it may be real. In particular, we see that the right lateral focal mechanism, the sense of the mismatch is opposite, or the rotation is opposite. And that would make sense if you have this kind of model where you have interlinked shear and dilational faulting. That is, in this case, the slip vector is, the orientation of the faulting, but the seismicity trend is the orientation that you would get if you connected these stars. So if you have these shear faults connected by these dilational jogs. And this is conceptually similar to this fracture mesh model that was proposed by Dave Hill back in the 70s. And there's reason to believe that these kinds of structures exist. We see them in geology. I'm not just completely making this up. This is an example from the North Island of New Zealand. There's a 1 meter scale bar here in the lower left. And these kinds of features have been the subject of a lot of geological investigation because they're often associated with, economic deposits of valuable minerals such as gold. But the interesting part for our purposes is that the faulting itself is likely an important part of the gold precipitation because of large pressure drops that are experienced by pore fluids on these non-planar fault systems. So this process is sometimes termed flash vaporization, and the idea is that you have slip on a fault that's not a plane. As you get that slip, you create cavities and you suddenly drop the fluid pressure. The fluid vaporizes, and that causes sudden deposition of dissolved silica and sometimes gold. And you can imagine repeating this process many, many times. That would be perhaps many, many earthquake swarms, and to create concentrated gold deposits. And there may also be implications of this process for the swarm dynamics themselves. And this is a plot showing CO2, and so the horizontal axis here is pressure. The vertical axis is the CO2 that's dissolved in the aqueous phase. And what happens is that as you get this pressure drop, so that's this arrow here, you start to form bubbles, CO2 comes out of solution. But if you restore the confining pressure, you can actually exceed the initial pressure because the CO2 does not go back into solution as rapidly as it comes out of solution. So this is like trying to put the cork back on a champagne bottle. It's harder to put the cork back on once it's been popped off. So it's possible that as you drop the pressure, dynamically during an earthquake, it could actually lead to an overall increase in the pressure and perhaps dynamically further drive swarm activity. Okay, looks like I have just a few minutes left here, but I want to go over one more example. It's what I would call a more typical swarm example. In this case, it's not volcanic. It's near the Makima Fault in Northern California. The Makima Fault is part of the San Andreas system. It's a right lateral strike slip fault. Accommodates a portion of plate boundary motion in Northern California. So in August of 2020, there was an earthquake sequence that initiated in this area with magnitudes up to 4.2. And, this is close to a major fault. So, people wondered, is this a concerning, is this possibly going to lead to a bigger earthquake? So partly for this reason, we wanted to take a look at this sequence in more detail. Okay, so this plot is showing a map view and a cross section of the routine earthquake catalog for this area. And you may not even be able to see the dots here. But essentially it's just a diffuse cloud of seismicity. The location uncertainties are as large as any location differences among these events. So essentially we have no information about faulting structure at this scale from the routine catalog. So we decided to apply the correlation-based detection and relocation to this sequence. We looked at mid-August through almost mid-December, about 117 days. There were only 388 routinely cataloged events in this area during that time period. But after processing, we were able to get more than 3,500 total events detected and relocated. So about 9 times the routine catalog. And this is what the sequence looks like. This is kind of intermediate between some of these swarms and a main shock aftershock sequence. We have that magnitude 4.2 occurred only about 9 minutes after the initiation of the sequence. And you can see it kind of decays with time, although we have some more bursts of seismicity over the next several months that I'll show have some kind of interesting spatial patterns associated with them. So this is what things look like after we detect and relocate seismicity. And you can see it's just night and day from compared to the routine catalog. So faults become visible. There's clearly complex structure. We see kind of this main zone that overall is striking toward the north-northwest, but we also see these northeast striking faults as well, especially activated. The warmer colors here are later in the sequence. So those are especially seeming to be active later in the sequence. And this is another case where we really would like to have focal mechanisms to resolve the faulting geometry. We can try to connect the dots with the relocated seismicity, but there are some cases where the faulting structures may still be ambiguous. So I talked about using the relative polarities to help constrain focal mechanisms. We can do that again in this sequence. But the other kind of data that's often used for focal mechanisms are S to P amplitude ratios. So we wanted to explore what could be done, in the context of this kind of correlation-based processing that we're using. What could be done to try to get S to P amplitude ratios for these events? So because the P and S radiation patterns are distinct, S to P amplitude ratios can provide a really useful constraint on focal mechanisms, usually in combination with P wave polarities. Unlike P wave polarities, it's not just up or down. The S to P amplitude ratios, have a number associated with them. But usually they require 3-component seismometers and relatively high signal to noise ratios. So we wanted to explore, what we can do when these conditions aren't met, and in particular, can we integrate this S to P ratio analysis into correlation-based processing? Well, it turns out that, we're already looking at P to P and S to S amplitude ratios between correlated event pairs. And we're doing this to estimate magnitudes of newly detected events. When we do the magnitude estimation, we're just averaging, all these amplitude ratios across the network, but we're actually throwing away a lot of useful information when we do that. So instead, we can take all those individual measurements and we can actually transform them into S to P amplitude ratios. And I won't go into the details of how we do that, but if you're interested, there's a paper in the seismic record that was published earlier this year. For this sequence, we see evidence that, again, there's complexity in the faulting patterns, and we see evidence that this complexity is reflected in the S to P amplitude ratios. So these top plots are showing the log S to P amplitude ratios that we're estimating based on these P to P and S to S to amplitude ratios. And these are, I should have mentioned, are computed on single seismic components. We use a smaller number of traditional S to P amplitude ratios to sort of set the scaling on these, but we're able to measure relative S to P amplitude ratios on single components. And you see, I've highlighted here two events C and D, at each of these two stations. These are the two stations that are highlighted here in the map on the lower left. And they have very different S to P amplitude ratios for these two events. At GWR, C has a much lower S to P amplitude ratio than D, and the opposite is the case at BARR. So these are two events, they're only about 120 meters apart. So this difference in S to P amplitude ratio is not a function of location difference. It's instead almost certainly a function of the difference in slip orientations for these two events. So we combine S to P amplitude ratios with correlation-based phase polarities. We cluster events that have similar patterns of polarities and S to P amplitude ratios. And then, like we were doing before, we compute composite mechanisms for groups of similar events. So in total, we finally arrive at mechanisms for more than 3,000 total events. So that's about over 90% of those 3,500 located events. For reference, there were fewer than 400 events in the original catalog, in the routine catalog. Okay, so we have focal mechanisms. We can start to plot, start to look at the alignment of the nodal planes of the possible fault planes from the focal mechanism with the alignment of seismicity. So this plot is attempting to do that. The upper left shows the full depth range. The other plots show increments of depth slices through the swarm. What these are showing is, these are dominantly strike slip mechanisms. So it's hard to show beach ball diagrams for 3,000 events in this kind of proximity. So what we're plotting is two lines, each oriented with the nodal plane orientation of the focal mechanisms, and with the length of rough approximation of the physical rupture dimension. This is great, but it's really annoying that the focal mechanisms have two possible fault orientations. So we wanted to take this one step further. I'm just about to wrap up here, but we wanted to try to resolve this ambiguity between the fault plane and the auxiliary plane with the focal mechanisms. So to try to do that in a systematic way, we did a stress inversion. We used the stress inverse algorithm proposed by Vavrikuk, 2014. And so that allows us to determine the likely fault plane among the two possible planes from the focal mechanism. So finally, here on the left are the likely fault planes plotted Again, the length of the line is an estimate of the physical rupture dimension, and these are color coded by the rake angle. So these red ones are dominantly right lateral strike slip. That fits with kind of the macroscopic orientation of the Makima fault. And then the kind of blue cyan ones are left lateral strike slip at what would be a conjugate orientation. These are both well oriented for failure in this kind of a stress field. Okay, so just to show a little bit of highlight a little bit of the complexity in the different depth slices here. This is a shallow depth slice, intermediate, and going toward deeper depths here. You can see quite different patterns at different depths. I wanted to particularly highlight this pattern here in the red box. If you were to look at this part of the faulting, the overall orientation is actually to the north-northwest, like the Makima fault. But when we look in detail, we see that most of the faulting here is probably happening on echelon faults that are oriented conjugate to that overall orientation. So instead of being north-northwest striking faults, they're actually a series of northeast striking faults. And instead of being right lateral faulting, it's likely left lateral faulting. So this is a pretty good example of, where these focal mechanisms combine with the relocated hypocenters to give us more information about the faulting structure. I'm going to skip this animation. It's basically the same thing. I can come back to it later if we want to. But I just wanted to, get back to this kind of fracture mesh model. Earlier I showed this Dave Hill model from his 1977 paper. Rick Simpson had a paper from the 90s that was expanding on some of these fracture mesh models. And essentially what we see here is this conjugate fracture mesh that he was, one of many that he was highlighting. And if we rotate this just a little bit, it essentially corresponds with this fracture mesh that we're seeing in this Makima sequence. Okay, last thing, just a little bit about this sequence initiation. I mentioned that it was, kind of intermediate between a main shock, aftershock sequence and a swarm. This first event was a magnitude 2.9. 9 minutes later, there was a 4.2 that was oriented with essentially the same orientation as the first 2.9. Over the first 2 hours, there were some aftershocks on the up dip part of this, what may be the same fault zone that's seemed to start to have kind of this fracture mesh, a mix of orientations. And we see that really develop over the next 24 hours, where we see development of these northeast striking faults, as well as this north-northwest striking orientation. So it's possible that this behavior indicates that there's some sort of fault valve behavior where this magnitude 4.2 is connecting a zone of higher fluid pressure regime than what previously existed on the up dip edge, and allows sort of that higher fluid pressure to propagate up dip and trigger events on faults with those conjugate orientations. Okay, so earthquake swarms, I hope I've managed to convince you, they're really fascinating beasts. We've learned a lot from them, but we also have a lot yet to learn. They at least have a lot of potential to tell us about crustal, perhaps fluid and earthquake dynamics. They can be generated by a variety of processes. Some of these are relatively rare, like caldera collapse and snowmelt infiltration. Some swarms are driven by aseismic slip, which is probably most common in subduction zones. I didn't get into that here. But most of the swarms, at least those that I've looked at, are likely driven primarily by fluid pressure perturbations. That's not to say that there can't be some component of aseismic slip but it's probably not the dominant process. So we see evidence for strong interactions between fluid pressure, fault slip, and permeability. We see overall trend for upward migration of activity, which may reflect upward migration of fluid pressure. And we often see complex fault geometries and perhaps hybrid shear dilational faulting. So like I said, we see, a lot of intriguing evidence. We're always, a lot of times this evidence is still circumstantial. That's the case of the evidence for fluids. I think it's pretty strong circumstantial evidence, but clearly there's still a lot that we have to learn, such as how, this vaporization process might play into swarm dynamics, and other aspects of this. So I think I'll stop there, and I look forward to any questions or discussion.
Thanks a lot, Dave. This is really a fabulous talk. I'll invite everyone to unmute and join me in thanking Dave for a really fabulous talk.